All right, before we get into our power series method, let's look at power series. All right, so let's say y, so solution y is going to be equal to, we find a power series, and so it's a summation, n goes from 0 to infinity. All right, so since coefficient is unknown, so I'm going to put the Cn, then say x to the n. Right? So this is the power series of the solution of the differential equation. And the great thing about the power series is that this is essentially a polynomial of infinite degree. So derivative is very easy to compute because it's just a power rule. So the derivative of this solution, so y prime, can be written as simply we just take the derivative, right? So term by term. So it's a summation. N goes from 0 to infinity, right? Cn is just a number. And using the power rule, you have an n in front. Then you have x to the n minus 1, right? And in this case, when n equals 0, so it's 0, term is 0 anyway, so there's no point of starting from 0, so we can start from 1. So we can turn it into 1, right? And then if you take another derivative, for example, second derivative is going to be same way, so it's a summation. N goes from 1 to infinity. Right, so n is just a number, and actually maybe I'll put the n here. N is just a number, and the Cn is just a number. If you take the derivative of x to the n minus 1, it's going to be put n minus 1 in front, then we subtract 1 from the power, so n minus 1 minus 1, so n minus 2. All right, and same reason. When n equals 1, this is going to be 0 anyway, so there's no point of starting from 1. We can just start from 2. Right? So those are the derivative, and it's very easy to find derivatives of power series because this is essentially the polynomial functions of infinite degrees. All right, so but we have to be careful about the power series since it's an infinite series, it might not converge to what we want. So it's nice to know the radius of convergence, and the radius of convergence can be found by taking a limit of absolute value of Cn over Cn plus 1. As n approaches infinity. All right, so let's look at the following example. All right, so we have a power series for e to the x, and let's try to see what the radius of convergence is. All right, so in this particular example, Cn is going to be, it's a 1 over n factorial. All right, so we just need to compute limit as n approaches infinity. Then absolute value, right? Cn is 1 over n factorial. Divided by Cn plus 1 is 1 over n plus 1 factorial. Yeah, we have that, right? All right, then this can be simplified as you have a limit as n approaches infinity. All right, so this is just basically double reciprocal. So you have n plus 1 factorial divided by n factorial. All right, but n plus 1 factorial is the same thing as n plus 1 times n factorial, right? So which means that we can cancel n factorial on the bottom, n factorial on top. So you simply get this. You have a limit as n approaches infinity of n plus 1. Right, we don't really need the absolute value because this guy is never negative. right? But you can see that here, this is going to actually goes to positive infinity, right? So therefore, the radius of convergence for this power series for exponential function is actually infinity, right? Which means that this power series converges to e to the x for all real number x, all right? How about the second example? If you have a 1 over 1 plus x, the corresponding power series is just summation n goes from 0 to infinity, x to the n. So in this case, Cn is equal to 1. Right? So if you do a limit as n approaches infinity of, right, you have a Cn is going to be 1, and a Cn plus 1 is going to be 1 as well. So this is just the limit is going to be 1. Right? So therefore, and the radius of convergence is going to be 1. Right? So this power series only works when x is between -1 and a +1 because the radius of convergence is 1. All right, that's it. I hope that this was clear.